The transformer architecture in deep learning is a neural network design centered around the multi-head attention mechanism, which involves converting text into numerical tokens and transforming each token into a vector via a word embedding table. This enables tokens to be contextualized within a context window with other tokens through a parallel multi-head attention mechanism at each layer, bolstering key token signals while reducing less pertinent ones. Unlike previous architectures such as LSTMs, transformers do not contain recurrent units, resulting in shorter training times. The absence of sequential processing in transformers, unlike RNNs, addresses a long-standing issue in neural network design, although it comes with the trade-off of computation time that scales quadratically with context window size. Methods for stabilizing training in transformer architectures include employing learning rate warm-up, where the learning rate gradually increases from 0 to a maximum value during the initial training phase before decreasing. Another technique involves using layer normalization before multi-head attention and feed-forward layers to enhance stability, eliminating the need for learning rate warm-up as suggested in a 2020 study. Pre-training fine-tuning approaches for transformers typically entail initial self-supervised learning on a broad dataset like the pile, then fine-tuning on a specific task-oriented dataset. Tasks commonly involved in pre-training and fine-tuning encompass language modeling, next sentence prediction, question answering, reading comprehension, sentiment analysis, and paraphrasing. The T5 Transformer report discusses various natural language pre-training tasks, such as reconstructing incomplete or corrupted text, language translation, and assessing the acceptability of natural language sentences. In evaluating language models, 3 primary classes of tasks exist: masked, autoregressive, and prefix LM. In a masked task, tokens are obscured, and the model predicts the hidden tokens based on context, aiming to minimize the loss function related to predicting these tokens. Models like BERT are trained for masked token prediction and other tasks. Autoregressive tasks involve initially masking the entire sequence, predicting tokens sequentially, with models like GPT trained for such tasks. Prefix LM tasks partition the sequence, where the model predicts tokens in the second part based on the context of the first, with models like T5 focusing on this approach. It's essential to note the distinction between masked in masked language modeling and masked in masked attention, as well as the difference between prefix LM, prefix language modeling, and prefix LM, prefix language model. Transformers consist of key components. First, tokenizers, which convert text into tokens. Second, an embedding layer, which changes tokens and their positions into vectors. Third, transformer layers, which apply multiple transformations to the vector representations, extracting linguistic information through both attention and feed-forward layers. 2 main types of transformer layers are encoder and decoder layers. An encoder processes input tokens consecutively, while the decoder processes both its own output tokens and the encoder's contextualized input token representations. An unembedding layer reverses the process of the embedding layer, turning vectors back into a probability distribution across tokens. Tokenizers play a crucial role in converting text to numerical data for the transformer model to process. The vocabulary size, N vocabulary, represents the set of tokens used by the tokenizer, with UNK typically representing tokens outside the vocabulary. Variants of tokenizers like byte pair encoding, word piece, and sentence piece are commonly employed. Each token is transformed into an embedding vector via a lookup table, connecting a one-hot token representation with an embedding matrix. The embedding vectors are summed with positional encoding vectors to create the input vector sequence. The dimensions of these embedding vectors are known as the hidden size or embedding size, DMB. The unembedding layer, on the other hand, converts vectors back into token probability distributions using a linear softmax layer. Weight tying may involve making the embedding matrix M and the unembedding matrix W transposes of each other. Positional encoding provides the model with information about token positions in the input sequence, crucial for processing the order of tokens correctly. It is represented by a fixed-size vector illustrating relative token positions and implemented through sinusoidal functions. Additional equations related to positional encoding are provided for viewing. The original article offers an in-depth understanding of these equations. Lastly, the feed-forward network in a transformer is a two-layered module that maps d-EMB dimensional vectors to other d-EMB dimensional vectors. These feed-forward layers contain the majority of parameters within a transformer model, incorporating weight matrices, bias vectors, and activation functions like ReLU. The intermediate size of the network is typically larger than the embedding size, for instance, in GPT-2 and BERT models. Each sequence consists of vectors with specific dimensions. By multiplying each vector from the query sequence by the query weight matrix, denoted as W to the power of Q, a query vector Q subscript I is obtained. The same process occurs for the key and value sequences, resulting in respective key, or K, and value, or V, matrices. Attention weights are calculated based on the dot product between query and key vectors, normalized using a softmax function. The output of the attention unit for a token is the weighted sum of all value vectors, based on the corresponding attention weights. Multi-head attention is achieved by combining outputs from multiple attention heads, allowing the model to capture varied definitions of relevance. The architecture of an encoder layer includes a self-attention mechanism followed by a feed-forward layer. This setup allows each token to attend to every other token in the input sequence without requiring causal masking. In contrast, a decoder layer incorporates a causally masked self-attention mechanism, along with a cross-attention mechanism to draw relevant information from encoder encodings. This prevents the decoder from using future output during prediction, facilitating autoregressive text generation. Various adaptations of the transformer architecture exist, with some models utilizing only the encoder or decoder components for specific tasks such as next token prediction or masked token prediction. The transformer architecture comprises encoder and decoder layers, each with their unique sublayers. In the encoder, two sublayers are utilized: self-attention and a feed-forward network. Conversely, the decoder boasts three sublayers: causally masked self-attention, cross-attention, and a feed-forward network. To enhance stability and convergence, residual connections and layer normalization, referred to as layer norm or LN, are implemented. The residual connection, expressed as y opposed to fx plus x, mitigates vanishing gradient problems by preserving input information during transformation. The sequence of operations in a standard pre-LN encoder-decoder transformer involves tokenization, embedding, positional embedding, layer normalization, multi-head attention, feed-forward processing, and final layer normalization for both encoder and decoder segments. Within the terminology surrounding transformer variations, distinctions arise among encoder-only, decoder-only, and encoder-decoder transformers. A brief overview of the pseudocode provides insights into the process. Encoder-only models map input text to vectors for tasks like text embedding, whereas decoder-only setups focus on text generation with causally masked self-attention and feed-forward networks. Prefix LM structures, a variation on decoder-only architecture with prefix masking, imply theoretical possibilities with nuanced mask forms. Additionally, mixed SEQ2-CQ models, exemplified by Google Translate's adoption of a transformer encoder RNN decoder model in 2020, reflect ongoing evolution and adaptation within transformer frameworks. Alternative activation functions in transformers have expanded beyond ReLU. For instance, SWIGLU was featured in the Llama series and PAL-M, while GPT-1 and BERT opted for GELU. These alternative activation functions are commonly paired with gated linear units in the feed-forward module. Regarding normalization techniques, options other than layer norm have been explored. RMS norm, as utilized in the Llama series, and methods like capsule norm, scale norm, or fix norm offer different approaches. Transformers may adopt varied positional encoding strategies rather than just relying on sinusoidal methods. While the original transformer paper implemented learned positional encoding, the preference towards sinusoidal encoding was noted. Notably, subsequent research revealed that causal masking within the architecture could effectively support absolute positional encoding implicitly. ROP, or rotary positional embedding, provides a unique perspective on positional encodings with rotational transformations of vectors. By applying specific angles to a list of 2D vectors, ROP encoding allows for location-centric dot products between vectors, emphasizing relative positions exclusively. Alibi, or attention with linear biases, diverges from the conventional positional encoders by integrating directly into the attention mechanism. It augments the attention process with linear biases intended to adjust attention distribution based on directional attribution. Alibi facilitates pre-training on shorter context windows before optimizing for longer interactions. Furthermore, relative position encodings, akin to Alibi, integrate additional positional nuances into the attention mechanism using a Toeplitz matrix to modulate attention patterns systematically. Efficient implementation of the transformer model in prevalent deep learning frameworks like TensorFlow and PyTorch has been instrumental in its widespread adoption. Notably, the Transformers library by Hugging Face has been pivotal in providing diverse transformer-based structures and pre-trained models. KV caching is a method used in autoregressive transformers during inference to preserve computed key and value vectors across attention blocks, optimizing the computational burden. Paged attention introduces memory paging enhancements to KV caching, particularly advantageous in scenarios like online chatbots, where efficiency during recurrent interactions is critical. Flash attention represents an innovative algorithm designed to streamline transformer attention mechanisms, especially on GPU platforms, enhancing matrix multiplication efficiency through optimized data handling strategies. Its evolved version, Flash Attention 2, further refines these techniques to accommodate complex language models and extended context lengths, catering to evolving computational demands. Flash Attention 2's improvements encompass refined work partitioning, enhanced parallelism, and support for diverse head dimensions, elevating processing speeds significantly over traditional attention implementations. The transformer landscape has seen notable advancements with the advent of multi-query attention mechanisms. By modifying the traditional multi-head attention approach through consolidated query projections, multi-query attention aims to streamline inference operations without compromising model quality. Notably, multi-query attention introduces innovative strategies like grouped query attention to optimize attention head allocations and enhance inference efficiency. Furthermore, the introduction of multi-head latent attention presents a refined approximation of standard multi-head attention models, significantly reducing computational overhead by streamlining key-value caching processes through latent space transformations. Speculative decoding strategies have surfaced as a viable means to expedite token decoding processes by leveraging predictive token generation followed by model verification mechanisms, aligning with the concept of faster verification relative to raw decoding in transformer architectures. Advanced concepts like multi-token prediction have redefined transformer paradigms by enabling continuous token prediction through iterative processing blocks, balancing speed and accuracy trade-offs effectively. Additionally, innovations in subquadratic transformers have addressed computational challenges associated with prolonged input sequences, offering optimized architectures like the Swin transformer and SepTR tailored for image and audio applications. Reshaping attention graphs through techniques such as the reformer and sparse attention models has revolutionized computational efficiency in transformer frameworks, emphasizing reduced computational complexities and enhanced model scalability. Noteworthy concepts like random feature attention and performer highlight, novel attention mechanisms leveraging randomized feature embeddings and Gram-Schmidt processed parameters to streamline attention computations and expedite inference processes significantly.